Okay, let's go ahead and get started. I'm Charlie Smith, the Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors from across the globe to catalyze a rapid, clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. The foundation of the GPST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support and standardization, and open data and tools. ESIG is the lead on Pillar 1, and more information on the GPST can be found at globalpst.org. As the lead on Pillar 1, ESIG would like to welcome you to the July monthly webinar of our joint GPST Pillar 1 ESIG webinar series. This series is an addition to the regular ESIG monthly webinar series and focuses on the GPST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both the founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and the research community participating in the GPST. An additional series of webinars on the other 4 pillars of the GPST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about the GPST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I would like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we use the Slido platform at slido.com. You need to open a browser window, go to slido.com, and enter ESIG25 as the event code. The instructions are also at the bottom of this screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, today's topic is on look-ahead security assessments and high IBR applications. This is a topic of increasing importance, driven by the transition in the resource mix from one of large fossil fuel and nuclear-based generation to one of largely inverter-based wind, solar, and battery resources. And here to tell us about it is Marta Escudero, a technical leader at EirGrid, the Irish system operator, in the future operations team of the Innovation and Planning Directorate. We're very fortunate to have Marta here with us today. She leads a team responsible for the development of new control center decision support tools for secure integration of high levels of IBRs. She's also an active SEGRE member and currently chairs Study Committee C4 on Power System Technical Performance. EirGrid is also a member of the core team of the GPST, and Marta is an active contributor. And as usual, I couldn't resist the urge to check out our common connections on LinkedIn last night, so I took a look. Even though we haven't worked together in the past, we do know each other, and we have 35 connections, with most of them through ESIG, GPST, ENSOE, and SEGRE, all citizens of the world. So today's webinar is titled Look Ahead Security Assessments, Operations Radar to Navigate High IBR Waters in the Journey to Net Zero. Operating with increased levels of IBRs introduces many technical challenges and increased operational complexity. Ireland is a small, isolated power system with limited HVDC ties. Because of this, the challenges are more pronounced, and new approaches have been developed to steadily increase the instantaneous share of non-synchronous resources, mostly wind, to the current level of 75%. You may remember not so long ago when it was only 50%. One of the key contributors to this success story has been the implementation of look-ahead security assessment capabilities as decision support tools in the control room. This webinar will share EirGrid's experience in the development and operation of look-ahead functionality for steady state and dynamic security assessment. EirGrid is a good member of ESIG and is punching way above its weight. I greatly value their contributions to GPST in the industry, and I look forward to what Marta has to say. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG25 to ask your questions. And without any further ado, let's go ahead and get started. Marta, I will now turn it over to you.
Thank you very much. Can you see my screen, the first slide?
Not yet.
Not yet. Okay, I didn't do it right then. So let's try again. Share screen. Okay, share that. And now.
Okay, it's coming up. There we see it. We see that box in the upper right.
What about now? Can you see the first screen?
Yes, we see the first slide now. Box is gone. Looks good.
Perfect. Thank you very much. Good evening, everybody from Dublin. And thanks, Charlie, for the kind introduction. And also thanks for inviting me to deliver this webinar. I'm delighted to be here talking to everybody about our new tool for look-ahead security assessments, and this tool is helping us to operate the power system in Ireland and Northern Ireland with increased levels of wind generation. It's allowing us to continue our path towards decarbonization of the electricity system. So I'm going to start today with a brief introduction of the Ireland and Northern Ireland power system for those of them who are not familiar with it. And then I will deep dive into the tool that we have developed for this dynamic security assessment in look ahead and real time. So talking about a background of where are we and who we are. So Ireland is situated in here. You can see in the map in the western part of Europe. We are this island, and we are facing the Atlantic Ocean. The location of this island is important because there's no protection from the waterfronts that are coming from the Atlantic. This situation is bringing us a lot of rain and a lot of wind that many people complain about, including me. But this rain is bringing us a beautiful and green Ireland, which I recommend people to come and visit. And the wind, we're actually harnessing and we're actually using this wind to contribute to produce electricity, renewable electricity, and contribute to the decarbonization of this energy sector. So the location of Ireland is very important. Who are we? Sorry, an EirGrid. We are the transmission system operators in Ireland and Northern Ireland. We have two jurisdictions, one single power system, one single island electrical system, synchronous zone, without any external AC connections. So Sony is the transmission system operator in Northern Ireland and EirGrid in Ireland. This map shows you the topology, the geography of the transmission system in Ireland and Northern Ireland. So in Ireland, we operate at 110 kV, which are these black lines, at 220, which are the green lines, and 400 kV, which are the red lines. So that's kind of our transmission mesh interconnected system. Northern Ireland in the north operates at 110 kV, the black lines, and 275 kV, the blue lines. Both systems are interconnected with a single tie line. Is a double circuit operated at 275 kV. And we have two small little links here in the northwest at 110 kV, which are used for voltage support on either side of the border, but they have very little transmission capacity. So we have phase shift transformers, PSTs, limiting the flows cross-border. So as I said, we don't have any AC interconnection with any external system, but we have two HVDC interconnections with our neighbors in Great Britain. Northern Ireland has an HVDC LCC interconnector called Moyle, 500 megawatts. And in the south in Ireland, we have EWIC, which is also 500 megawatts, but this one is VSC technology. So one single synchronous system, two system operators. We operate the power system as a single electricity market. We have two control rooms, one north, one south, and switching and control of the transmission system is done on a jurisdictional basis, but scheduling as dispatch is done on an all-island basis, alternating north and south responsibilities in the control rooms. Our demand, our peak demand is around 7 gigawatts. It's a winter peak demand. And the minimum demand is about 1/3 of that, and of course in the summer. In terms of generation, I'm going to talk about wind, but here we talk wind and renewables. We more or less is synonymous, one or the other. So we have a installed wind capacity of 5.9 gigawatts, and we have a peak wind generation of 4.6 gigawatts that happened last year in February 2022. Other fuel mix, you can see it down here on the pie chart. So in 2020, we had overall 42.5% of our electricity consumption came from renewables. Most of it was coming from wind. And the rest of that came from burning fossil fuels, mostly gas. So here, similar to many other parts of the world, we're undertaking an energy transition. We're moving towards decarbonization of the electricity sector. And this is kind of a long process. We started around 2010. We started with operating with or running with about 10% of our electricity consumption came from renewables back in 2010. In 2020, we moved from that to 40% of our electricity, or more than 40% came from renewables. All of this didn't happen from one day to the next. There was a huge amount of work conducted over those 10 years. There was a big program of work called DS3 that put in place all the steps, all the measures that allow us to increase gradually the level of renewables that we can operate in real time. And dynamic security assessment and real-time security assessment was one of those measures that were implemented, and I will describe the tool that enable us to move to this high levels of integration of renewables. But this is not the end of the road. 2020 is gone past now, and we have a new target for 2030. The government has mandated us to operate or to enable that up to 80% of our electricity comes from renewable sources. Long-term end of the road in 2050 will be net zero. How do we will get there? There is also a big program of work that maybe we can talk about other day in another webinar. So that's kind of a brief introduction of where we are, what is EirGrid and Sony, what do we do? And now I'm going to deep dive into the tools that we have developed in order to allow us to assess the dynamic security of the system in both real time and look ahead. But before I go into that, I want to talk a little bit about the terminology that we use, make sure that we're all clear. So we start with the term of system security assessment. And what this concerns is the analysis and quantification of the capability of a system, a power system in a particular state to withstand imminent disturbances or contingencies and remain within parameters, within defined criteria. So in terms of security assessment, we could talk about static security assessment or SSA, and this analysis deals with two different states before and after the scenario, the disturbance, but both steady state analysis. We also have a dynamic security assessment, which looks at transition between those two states, between the pre-disturbance and a separate and a different state post-disturbance. So within the dynamic security assessment, we could be talking about voltage security, transit security, or small signal stability, depending on what particular phenomena are we looking or what is the phenomena driving the insecurity. And the tools and methods and the models that we use to assess each of those different levels of security, they're different, and different tools, different models. So we are going to concentrate on DSA, Dynamic Security Assessment. And here we can expand more terminology. So we could be talking about offline security assessment, dynamic security assessment. And in offline mode, the user creates all the scenarios, set up the models, creates and defines how the scenario is going to run, how the simulations are going to run. They could be run triggering them manually, or could be run possibly on batch mode, but it's always under the user intervention. On the other side, we have online DSA, in which everything is running automatically without any user intervention. So the tool in the background sets up the cases and triggers the runs, produces the results, and displays this in a manner that the user can kind of very easily interrogate them and get the information that is required. Within online DSA, we could be talking about real time, and here the scenario that we are assessing for dynamic security is the right now in the power system, right now. And we do that by using the state estimator solution from EMS with all the SCADA telemetry. So we have a very clear picture of the power system state as we speak. We could also be talking about look ahead DSA. And here we're assessing not the real time, not the right now, but forecasted scenarios, forecasted states of the power system in the near time, looking based on market schedules, based on the expected topology of the network. So the tool that we have developed recently and that is operational in the control rooms, both in Northern Ireland and in Ireland, ticks most of the boxes in this screen. So we have a security assessment, both static and dynamic. We are assessing voltage security, and we're also assessing transit security. We are not looking at the small signal on the tool itself, but we have the capability to assess that in offline mode, not integrated on the tool, but in the back line. And we also have online functionality for real-time assessment and also for look-ahead assessments. The tool also allows offline study mode capabilities. So where are we with DSA? So we have been working with and using DSA applications for a very long time. This journey started back in 2009, where we started a pilot proof of concept project with PowerTech in Canada using their DSA tools application. So out of these pilot projects, we developed a tool that we call it WSAT, stands for Wind Security Assessment Tool. And this tool, as I said, went live in the control room in Dublin in 2010, and it was assessing the real-time dynamic security of the power system of Ireland only. Northern Ireland was represented as a network equivalent. In 2012, we extended the functionality of WSAT, and we represented in detail the all-island system, Northern Ireland and Ireland. And the functionality was also, the tool was also deployed in the control room in Belfast. At the time, we were running DSA analysis every 15 minutes until in 2016, we undertook a hardware upgrade and we improved the solution time from 15 minutes to 5 minutes. All of that was, the tool was called WSAT, and again, we were running only real-time security assessments. Then we started a new project for a brand new tool, which was based on the old WSAT, but it was a completely different tool that we completed, and we went live with it in December 2010. This new tool was called LSAT, based on WSAT, still using DSA tools. But the functionality of this tool was enhanced and extended. We were looking at real-time and also look-ahead security assessments. This was a brand new tool, and confidence on the outcomes of this tool have to be built. So for a couple of years, the tool was operational in the control room, both Dublin and Belfast, but it was running side by side with WSAT. We didn't retire WSAT straight away. So the control room operators had the assessment from both tools, and most of the times were matching, which is great. We built the confidence gradually, and we finally retired WSAT early this year after a long period of service. So we may ask ourselves, why look-ahead capabilities? Why do we need them? So as I said, we have been using DSA capabilities application for a very long time. And this capability has supported the increase of integration of renewables, the wind in our power system. Back in 2010, we were operating with a level of renewables which we measure with a metric. We call it system non-synchronous penetration, SNSP, which gives a measure of the instantaneous level of demand that is met with non-synchronous resources, which in our case are mostly wind, but we also have a little bit of solar, and then the HVDC imports. So back in 2010, we had a limit of around 50% of SNSP. The integration of WSAT in the control room has enabled us to gradually and in smaller steps increase up to 65% SNSP. During this journey, we learned a lot. We learned that by experience that operational complexity really increases as you increase the level of non-synchronous renewables and you increase the level of wind. Stability of the system is a big challenge. And as we increase the level of wind on an instantaneous basis, the number of correction actions that we can implement is reduced as we displace conventional units with wind. And the time that it takes to implement any remedial action is actually increased. So it takes time if you need to bring a new unit online, a new synchronous generator, bring it up to speed. It also takes time if the remedial action that you need to implement is sectionalizing the network, changing the network topology. So all of those measures take a little bit of time. So based on experience, based on intensive studies offline, we identified that in order to increase with confidence the SNSP level above 65%, we needed to have forward-looking capabilities. We needed to have dynamic security assessment, not only in real time, but also in the incoming hours. So that will give us the time and will let us kind of get ready and implement the most effective correction action in a timely manner and identify which is the most cost effective as well. So with this functionality, with this new tool, we currently have increased the level of SNSP, and we're currently operated at 75% SNSP, which basically what it means is that in any particular moment we could be meeting our demand, 75% of our demand only with wind or HVDC imports. So what is LSAT? LSAT in a nutshell stands for Look Ahead Security Assessment Tool, and it's just an online application that monitors voltage security and transient security on the transmission system in both real-time and look-ahead timeframes. The key features of this application is that it incorporates full integration between EMS and DSA in the two different environments. So in EMS, we have a GE Itera application, and in the DSA, we have continued with PowerTech DSA tools application. In addition to the full integration between EMS and DSA, this tool has interfaces, complex interfaces with other applications like the market management system and the outage management system. Critical requirements of this tool are availability. This is a critical operational tool, and we need a very, very high level of availability and reliability. And we have achieved that by implementing redundancy in the DSR servers and all the data transfers. So we have a duplicate set of servers in two different sites, and they're running 24/7 in sync in both sites. And what this means is that if one set of servers, if LSAT main it's unavailable for whatever reason, something happened in one site, we can transfer immediately operations to the other site, and we don't have any delays in the startup of applications or any other potential issues there. Speed is another critical requirement, and we have achieved that using high performance servers with a very large number of cores. And our DSA tools use distributed processing techniques that run in lots of multiple kind of simulations in parallel. Accuracy is also a critical requirement. So how do we guarantee this? So before we roll out this new tool, there was a huge amount of effort in put into validation, making sure that the results were fit for purpose and that they were accurate enough. We validated against WSAT. We're also conducting regular monitoring of all the inputs and outputs of the tool, and we conduct regular validation of the tool outcomes against system incidents, against actual measured data, which is the proof, the final proof of accuracy. Visualization is also a very important requirement, and here the key is that they present the results to the user, to the control room operator in a clear manner, intuitive manner, that it has no room for error, and we only present what is essential, the minimum information that is really necessary, and not overload with lots of useless or confusing information. And the final requirement is archiving. So we need all the inputs and outputs of the tool to be archived and to be fully available at any time for offline analysis or for auditing purposes. Just remember that we're using this tool for making decisions in real time, decisions that sometimes involve changing the market schedules, constraining down generation, and this has to be traced back, and we need to kind of be able to justify all those decisions. So what does LSAT? The main functionality, it has an online real-time and online look-ahead functionality. So these are the main key functions. This is the core of the tool. Both online functionalities run automatically. Real-time looks in at 5 minutes intervals. look ahead, the user can select the period and the frequency of those runs, but by default we have selected it to run on every hour, and it's assessing 10 time points in every hour. It's giving us the information of the next 10 hours, how the system will look like. The online real-time assessments start from the EMS state estimator solution. Again, it's giving us the right time right now, whereas the look-ahead assessments, they're based on market schedules and outage plans. They are our best prediction at the moment on what the system is going to look like in the next hour, the next 2 hours, etc. But in addition of this online functionality, the tool also has the capability of conduct offline studies. So these ones are manually triggered by the user. The user has full capability of select the periods that we want to analyze. And the user has the capability also to select alternative generation schedules and alternative outage plans. So this slide is going to give us just a graphical view of what the time frames of interest for LSAT are. So we have here at the top left, we have a view of the dashboard. At the bottom, we have a timeline, which is not at the scale. It gives us the right now. Let me see if I get the pointer here. Laser, yes, here we are. So this is the right now. The immediate past up to 5 minutes, and the future we have all the different market trade periods up to the day ahead, up to normally maximum of 30 hours ahead. So what does LSAT real-time dot is giving us an assessment of not the right now, but the immediate past. So we receive the state estimator solution every 5 minutes. It takes a little bit of time for the tool to process all that information and do all the calculations, typically about 3 to 5 minutes, and then we have the assessment. So when we're talking about real time, we're talking about quasi real time. It's just the very, very immediate past. So that is what real time looks at. And then look ahead is looking at a range of different time points in the immediate future. So the user can select whatever market trade period that wants to assess, whatever is interesting. It could be the early morning load ramp up. It could be the evening load ramp up as well. But normally, just by default, the user the control rooms are looking at the next 10 hours just in sequential order. Even there is the capability of look at alternate points. They're just more comfortable looking sequentially hour by hour. In terms of performance, the performance of the tool is highly dependent on the size of the model. So our model, our system is not massive. So our model is a moderate size. We have 1,500 buses. We have 420 generators, 850 lines, 900 transformers, 650 loads in our model, and we have 2 HVDCs, 1 LCC and 1 VSC. So with this model and the hardware implementation that we have in both sites, we have a real-time performance of 5 minutes per cycle. Most of the time, it's completed in way below that. About the average is about 3.5 minutes per cycle. And look ahead, we have a maximum performance requirement of 3 minutes. Again, that normally exceed that performance, and we complete the computations in about 2.5 minutes. This this slide gives us an schematic of the data flow process within the tool in real time. So if we start from, we have 2 different environments. We have EMS and DSA, and they're fully integrated through data transfers. In EMS, we start from the state estimator solution, which is conducted in EMS. There is an application that converts that solution from node breaker to bus branch format. and it translated into PSC version 30 raw format. Then we also export SCADA signals, contingency definitions, and generator reactive capability curves. Sorry. All those files are exported as flat files and exported into DSA. And they are captured by an application called DPS, which is been developed in-house by us, and it runs Python, and it does a little bit of data processing, but basically the main function is data management and send the data files, receive the data files, and transfer them to a location where DSA can start processing it. So when they are transferred to that location, the first thing that happens is that we run an application that's called PFMod that incorporates a number of data into the load flow solution from PSC. The PSC file that comes from EMS doesn't have a detailed HVDC model. The HVDCs are coming as proxies with dummy loads and dummy generators. So that is replaced here by a detailed HVDC model. And a load flow solution, a new load flow solution is reached, and the file is converted into the format that DSA tools requires in PSAT. We have a load flow and a number of ancillary files, which are used by two applications, VSAT for voltage stability and TSAT for transient stability. These files are combined with a number of other configuration and model files that live permanently in DSA. Once the computations are completed, voltage and transient security, the results are sent into a dashboard where we can have all the reports, plots, history, and we can access all the files and conduct additional offline analysis. And the loop is closed by the capability of sending alarms back into EMS results and alarms. So this is real-time functionality. So look ahead is very similar, but rather than starting in EMS from the state estimator solution, we have a different application called RMTNet that generates a series of load flow solutions, starting from data from an external system, from the market and from the outage management system. So we input the generation schedules, the HVDC schedules, the load forecast, and the plan outages. So all of that is combined by this application, RMTNet, and it generates a series of load flow cases in PSC raw format in version 30. All of that, again, is transferred into the DSA environment, and the process is exactly the same as in real time. We get our results in the dashboard, and we close the loop with the capability of sending alarms back into EMS. I'm just going to talk a little bit about the two security assessments that are conducted, voltage security and transient security. So voltage security is conducted using the VSAT application of DSA tools. So it's based on a series of load flow simulations, starting from the base case, and we also conduct transfer analysis. Transfer analysis stress certain corridors or certain variables. So one transfer is maximizing the amount of wind that we can incorporate into the system. So we scale the wind up, and we scale down the conventional generation. And that will give us, we run that series of simulations, and we identify which is the limit, the maximum limit of wind. So this tool also uses the contingency list that is imported from EMS, where the grid controllers have the capability of enable or disable certain contingencies depending on the operating conditions at the time. By normally, this is about 900 contingencies that we run in VSAT. VSAT also take into account the reactive capability curves of each generator. So when we're scaling wind or conventional generation up and down, the reactive capabilities, the limits, they are adjusted accordingly. Any protection schemes are also represented and captured in the simulations. And basically what we want to know out of this analysis is the base case secure, is the right now secure, and what is the distance to insecurity in case that we are secure now, and what is the maximum level of wind that I can incorporate in the system. So that is all those kind of answers are presented in the dashboard. And one of the other type of solutions or type of displays that the tool produces a graph like this, where it's giving me the maximum amount of wind at different points in time. So here the blue line represents the wind forecast. The white line is the wind, the wind output that we have in real time in the system, and the red line just indicates what is the maximum limit that we can incorporate before we start breaching security criteria. Another type of analysis that the tool conducts is transit security analysis. And here is not load flow analysis. Here we use phasor domain simulations, time domain simulations. So the models that we use are a combination of generic and user-defined models. The time domain simulations is very computational intensive, so we're trying to increase efficiency with the models and try to use as much generic, but with site-specific parameters as possible. We run a series of contingencies that are defined and live within the DSA environment. So currently we're running about 800 of those contingencies, and they run up to 15 seconds. So this, as I said, is computationally intensive, and we have some features which identify whether the case is secure, that is looking at the rotor angles, and if it identified after a couple of seconds that the rotor angles are not, the distance between the angles is not increasing, it just kind of deemed the contingency secure, and it doesn't run out of the 15 seconds. So this efficiency kind of allow us to run this level of contingencies. So what we're interested to know out of this assessment is, are all the synchronous machines still synchronized, or have we pulled asleep some of the units? And is the frequency stay within limits in terms of amplitude, the nadir and the zenith, and also the rate of change? In case of that we have any rotor angle insecurity, if a synchronous unit pole slips, so the tool will present as, or will suggest preventive control actions. And this is a view of the dashboard. As I said, that we're trying to make it as intuitive as possible and present only in the main dashboard only the information that the grid controller needs in order to make a quick decision. So that's there showing us the real-time assessment, and we have a traffic-like system, which just both green means that it's secure both for voltage and transient stability. The next on the right-hand side, it gives us the look-ahead assessment. So we can, this is basically the same information, but point by point into the time frame of interest. The next part of the dashboard, it gives us a summary. So if there was any insecurity, we just go and select that scenario, and it will give us a summary. If there was any insecurity, it will give us more information. Then we have the transfer analysis summary. The dashboard also gives us an indication of the timestamp of the scenario that we are assessing. Give us some information about the cycle that is in process. So this one kind of has run in 2 minutes and 11 seconds. And we have access to, if the user is interested in find out a little bit more about that particular scenario, can go in those buttons, give access to more detailed report and analysis tools. We also have a frequency summary display that I will show you in a minute, and access to the offline analysis tools. This is one of the most important screens that the tool is providing us. It's giving us a summary of the frequency performance of the system, both in real time and in look ahead. So it gives us a summary of the frequency of the worst case scenario contingency, both for nadir and zenith, and plus positive and negative rock-off. And it gave us, we have two sub-screens. One is for all contingencies except for system separation, which is the most critical contingency for us because we only have one timeline between north and south. So it was considered that it was important to separate this contingency on its own and produce the results in graphical format. We have the limits, the amber alert and the red alert. And if we exceed those limits, the table here will show us with the color in orange or in red as well. Yes, kind of that's in terms of the tool, I described the functionality, but an important feature of the tool is that we need to rely on we need to trust the results that are produced by the tool. And in order to do that, we conduct validation of the models. So the best way of validating the models is comparing the outcome of the tool against recorded events. So we have a defined process in which we gather information, we select the incidents that we consider interesting. We gather the recorded data from PMU. We gather also the historical cases from LSAT, and we set up the cases, we conduct the simulations, and we perform the analysis to identify whether the models perform as expected or they were not adequate. So here is an example of one of those model validations. And what we see is that the original model was underperforming. The nadir was severely underestimated, giving the grid controllers a false sense of security. In reality, the nadir was much lower than the model predicted. So we look at this scenario in detail. We look at every single of the models. We have the PMU data recorded at the terminal of the most critical or the most important locations in the system, at the terminal of generators and large demand. So all that information give us sufficient data for improving the models. So we did a little bit of tuning in this particular case, and we managed to match the measured data very well. These tune parameters are also checked against many other incidents, and that's how we progressively improve the models and get confidence in there. Just kind of very quickly share some of our experience with the tool. So just probably goes without saying, but the assessments of the tool are only going to be as good as the data that you feed. So the starting load flow case is critical. For real time, the starting point is state estimation. So because we have very good observability of our transmission system, these solutions are generally very good. In look ahead, on the other hand, the solution is produced with a different application. It's a prediction, and sometimes getting a good solution could be challenging. Special attention needs to be taken to the voltage regulation settings. How do we define our schedules, the voltage control schedules, make sure that there are not contradictions, that the controls are not haunting. And also very important is how to define the outages. So the tool is only going to work with the input data. So it's very important that when the outages are defined, that the circuit breakers are introduced correctly. So when this is translated into the tool, into a load flow model, it represents accurately the topology that will happen in the system. Other areas that kind of maybe to comment is the arming of special protection schemes and other model parameters. So in real time, we're receiving the signals directly from SCADA. So the models are reflecting exactly the status of the protection, the status of the control systems that are happening in real time. For look ahead, we have to estimate how these controls are going to be, whether they're going to be in service, out of service. So we have implemented that logic with Python. It's a script that is running and is updating the dynamic models in also dynamically with the estimated parameters. Some words about the model upkeeping. So one thing that is very important is that we're receiving models from EMS. It's very important that the files that are residing within the DSA, that they match, that there is consistency in the naming and the numbering of the buses and all the equipment. If there's no match, the solution is not going to be correct because that model is not going to be taken into account. So it's also to mention that here in Ireland and Northern Ireland, we are experiencing a lot of activity in the industry. We have a lot of new connections, new wind farms connecting very frequently, new solar farms. So all the models have to be updated very, very quickly and keeping a pace between DSA and EMS. We also conduct regular reviews to make sure that all our protection schemes and all the contingencies are really reflective of what's happening in the system. And just to mention that it's critical that all of this is tested in a production in pre-production environment using live data feeds. So it's not the same to test and try to initialize a model in offline, which it may initialize for that particular scenario, but when you feed these models with live data, you throw live data to it, anything could happen. We need to make sure that the models and the simulations are robust to capture and to deal with all of these different type of data. And finally, just mention that we have a dedicated team looking after this data, looking after this tool. And yes, a word of advice that do not underestimate the effort required for this model upkeeping is critical. The tool is only going to give us results based on the input data and the model. So it's very important that we dedicate enough effort and time to maintain them. We have been using this tool, DSA, for over 12 years now, operating 24/7. It's very robust, and we have gained a lot of confidence on it. I'm not going to lie, it wasn't perfect from day one, but improvements have been introduced over the years, and now there is great confidence and great acceptance on the tool. A couple of words about the project, the LSAT project. Interestingly enough, COVID hit us in the middle of it, so we delivered the project during the lockdown. The project was everybody was working remotely. We have a large team of multidisciplinary skills and cross-functional people. So the team also was geographically dispersed about multiple time zones. We have Power Tech in Canada, we had GE in Paris, and we had people in Belfast and in Dublin. Communication, logistics was very important and tricky, but we went through that. We learned through the project that new and very complex interfaces were required, and they were implemented. This project also represented a very step change in computing power requirements with respect to what we had before with WSAT, which only computed online in real time. So now we're talking about real time plus look ahead. It was a massive increase in hardware requirements. But all in all, we had an excellent team. We had an excellent support from the two vendors, from GE and PowerTech, and we couldn't have done it without them. So if they're listening here, thank you very much, guys. In terms of our operator experience, we before rolling out the new tool, there was training provided to all the new the grid controllers, and on top of that, we conduct periodic refreshers, so we keep them kind of in their toes. We're also seeking feedback continuously from the grid controllers. We need to hear about what they see in the tool, whether they suggest any improvements, whether something is not working, so we can address it. But all in all, confidence on the tool has been built over time, and now there's great acceptance on it, and actions are taken on a regular basis in the control room based on the outcomes of the tool. Just to finish up, just mention a couple of benefits that the tool has given us. So this tool provides a radar-like guidance on how to operate our power system in a safe and secure manner, while minimizing wheel curtailment is a very important aspect of it. It helps us to maintain the power system security under all conditions, including abnormal scenarios that may not have been captured in offline analysis. And this tool has become a critical decision support tool that allows us pushing the boundaries, relaxing the constraints, and allow us to integrate more renewables in real-time operations with high confidence. We're currently operating at 75% SNSP. We have also recently changed our standard of ROCO from 0.5 to 1 hertz per second. And we're currently running a trial with a reduced number of synchronous units. We're not running with 7 units in all island bases. So this has not been the only the determinant factor, but it's a key contributor. LSAT is helping us to meet our government renewable targets. And this is all I have for you in relation to LSAT. I want to thank everybody for your attention, and I hand it over to Charlie.
Well, that was an awful lot that you had for us, Marta, so thank you very much. It was a whirlwind tour. We've got a lot of questions. There's just about 40 questions. We're short on time, so I'm going to let the questions run over 5 minutes. So instead of stopping at the top of the hour, if I could ask your indulgence and run over 5 minutes so we can get through a couple of the top questions anyway. Is that okay with you?
Yeah, that's perfect. Yeah.
Okay, good. So I'm just going to jump right in. The top question here is, how do you assess stability concerns with IBRs during weak grid conditions in real time?
That is a very good question, Charlie, or whoever posed that question. And the answer is that we don't assess weak conditions in real time just yet. We are monitoring. We have a kind of extensive rate of PMUs that we are monitoring what is happening in the system in real time, but we don't have the capability just yet to assess or determine when the strength of the system is not sufficient, and we have a risk of starting with instabilities, control interaction, etc. We are starting to look at that. We are working with partners, and we're going to continue looking into that. And for next year, it's one of our priorities to determine, to come up with metrics that are going to allow us to identify risk of insecurities due to weak grids, and determine what is the right tool and the right models to assess that. Everybody is talking about EMT, and I'm a big believer on EMT, but currently EMT capabilities in real time is not feasible. So we need some sort of a screening process metric that tell us this scenario is really risky. This is what you need to analyze in EMT, and maybe run it offline. The technology for running this online is not there yet, maybe in 10 years' time, but I don't know if that answers the question.
Okay, you must be looking into a crystal ball, Marta, because the next question is, how do you assess the need for an EMT-based dynamic security assessment?
Again, not just yet. It's a project that we are starting, and hopefully in maybe 6 to 10 months, I'll be able to give you an answer. But for now, we don't do that. No, we're just monitoring with our rate of PM news, and we keep a very close eye on what the system is doing.
Okay. And a follow-up question from Ilya. How is the small signal stability assessment conducted with such a high share of renewables and various converter models?
Interested? Yes. So we don't do a small signal stability analysis very regularly. We do it when we see the need. So we have been observing very low frequency oscillations in the system for a number of years, and studies have been conducted with small signal models to understand that behavior and try to come up with remedial action, with mitigation solutions. And yeah, that's been conducted, but offline. I'm not sure if the question goes in the area of what models are used. Are we using black box models? How are they linearized? So no, the models that we're using for this analysis are generic.
Okay. Do you check the fault ride-through capability of IBRs in the online assay?
Do we assess the fault ride-through capabilities? So the customers, before they connect, as part of the connection process, they have to do a number of assessments, they have to do a number of studies, and they have to demonstrate to us that the plant is capable of riding through faults according to the grid code requirements. And they need to provide a report with that assessment, and they need to provide the models that match that assessment. So that is a pre-connection as part of the assessment process. In real time, we don't do a specific fault right through assessment, but we simulate faults at many different locations within the system and faults of different durations. So that is intrinsically measured there. And yes, some faults, some wind that is nearby will trip, but we're looking at the overall system security. We're not really, if we lose a couple of wind farms, well, it's not a risk. If there are small wind farms, it's not a risk to the system.
Okay. Here's an interesting one. What will you need to do to get from 75% to 100% SNSP?
If I knew.
If you knew, you wouldn't be there.
Well, I will probably be here trying to implement it. But yeah, we have started a big program of work, which is called Shaping of the Electricity Future. And this big program of work have different pillars, and they're looking at all the different aspects that need to be considered, and in particular going from 80 to 200%, we probably need new technologies. Probably grid forming will be one of those, maybe not the only one, but yeah, there is a lot of changes that need to happen, both in terms of technologies, maybe in terms of operational practices, grid code requirements, new tools. If we're talking about new phenomena that arises with those levels of renewables, of inverter by resources, maybe phasor domain is not the right tool. Maybe we need to look at that as well. But yeah, there is a lot of work that needs to be done. I don't have all the answers yet, but we have a little bit of work to be done to get there.
Okay, I'm going to skip around just a little bit. So considering all uncertainties, do you feel a need in probabilistic DSA?
Yes and no. It could potentially bring benefits. I don't see the need right now, since with the performance and with the capabilities that we have now, we are already running the most severe contingencies, and we're starting from the real state of the transmission system. So if I didn't have the online capability, if I was running offline, yes, definitely the probabilistic approach will have a lot of benefits. But given that I'm starting from a not uncertain position, I'm not sure. I'm open to suggestions, but I'm not sure that it will give us that extra benefit.
Okay. I want to take one last question. This fellow has been waiting for a week, Dennis, and the question was in the Slido when we opened it up, just to reward him for his patience. What new organizational capabilities, rather than individual capabilities, do you see as critical to building and operating the future smart power network?
Wow, that's a big question. So Dennis, there are a lot of answers there, and we could be talking for days, but operational capabilities, so multiple areas in every. I see that the skills that we need are different. So we are moving to new technologies. We are moving from operating a system dominated by synchronous generators, where we fully understood the physics behind those. We're moving to a new world where the behavior of the dynamics of the power system are going to be determined by power electronic controls. So the old-fashioned people like me were not experts in power electronics, so we need to build up this capability coming from the new generation, from the graduates. We also need to kind of change or probably enhance the way we work, maybe more cooperative, more dynamic. Decisions need to be made in a more agile manner. We need to get more kind of proactive with IT solutions. We need not to consider our system as a silo. We need great collaboration with our distributor system operators. So there is a wide range of operational capabilities that need to be developed. It will take days to go one by one. I don't know if that answers superficially the question.
That's a work in progress for sure.
Definitely.
Okay, we're running a little over as I said, so I think we're going to need to go ahead and wrap it up. Marta, I want to really thank you for this very informative and forward-looking webinar to help us get ready for operating systems with a very high share of IBRs. You're pretty well along that road. And as I mentioned earlier, an email will go out once the video file has been posted. There's still a lot of questions we didn't get to, and we're going to take advantage of the good graces of Marta to go ahead and answer those questions and get them posted as quickly as possible. So we appreciate everyone's engagement, and if you would like to stay engaged, I would invite you to participate in the next ESIG webinar on August 10th on marginal emission rates and their application in voluntary clean energy investments with Hank He of Tabors, Karaminas, and Rudkovich. I'd also like to invite you to attend the ESIG Fall Technical Workshop in San Diego the last week of October, and I can assure you that you won't be disappointed. Further information on all of our webinars and events can be found on our website at esig.energy under events, and you're all invited to attend. Information on all of the GPST webinars can also be found at globalpst.org. Marta, I want to thank you again for this very timely webinar and thank all of you for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. Bye now.
Thanks.
Good night, Marta.
A pleasure.